What if the universe is hiding secrets so profound that even our most advanced science cannot unravel them? Picture this, a force so powerful it bends galaxies, yet invisible to our eyes. A burst of energy so intense it lights up the cosmos for mere milliseconds, leaving scientists scratching their heads. These are not the plots of science fiction. They are real mysteries lurking in the vast expanse of space. Today, we dive into the top 25 astronomical phenomena that continue to defy explanation, phenomena that challenge everything we think we know about the universe. From the invisible grip of dark matter to the eerie silence of the cosmos despite the high probability of alien life, these mysteries remind us just how much we have yet to discover. So, buckle up and prepare to explore the unknown, because by the end of this journey, you'll see the universe in a whole new light, one filled with wonder, curiosity, and the tantalizing promise of the unexplained. Now turning to the first phenomenon on our list, we encounter one of the most perplexing mysteries in modern astrophysics: dark matter. Imagine a substance that makes up about 85% of all matter in the universe, yet it remains completely invisible to us. Dark matter doesn't emit, absorb, or reflect light, making it impossible to observe directly with telescopes. So, how do we even know it exists? The answer lies in its gravitational effects. Scientists first inferred the presence of dark matter when they noticed that galaxies were rotating faster than they should based on the visible matter alone. Without the gravitational pull of dark matter, galaxies would simply fly apart. This invisible force acts like cosmic glue, holding galaxies and galaxy clusters together. But what exactly is dark matter? Despite decades of research, we still don't have a definitive answer. It could be made up of exotic particles that interact only weakly with ordinary matter, or it might be something entirely different that we haven't even imagined yet. To uncover its secrets, scientists are conducting groundbreaking experiments. The Large Hadron Collider, for instance, smashes particles together at incredible speeds, hoping to produce dark matter particles in the process. Meanwhile, specialized detectors buried deep underground are searching for faint signals of dark matter interacting with ordinary matter. Yet, despite these efforts, dark matter continues to elude us, reminding us just how much we still have to learn about the universe. As we move forward, this invisible enigma remains one of the greatest challenges in our quest to understand the cosmos. Now turning to the second phenomenon on our list, we delve into another cosmic mystery that challenges our understanding of the universe: dark energy. While dark matter holds galaxies together, dark energy is the mysterious force responsible for the accelerated expansion of the universe. Imagine a force so powerful that it counteracts gravity on the largest scales, pushing galaxies apart faster and faster over time. But how did we discover this enigmatic force? The answer lies in the light of distant supernova. In the late 1990s, astronomers observed that certain supernova, known as Type 1a, appeared dimmer than expected. This dimming suggested that these exploding stars were farther away than they should have been, indicating that the universe wasn't just expanding, it was expanding at an accelerating rate. This groundbreaking discovery led to the realization that something was driving this acceleration, and that something was named dark energy. Today, dark energy is thought to make up about 68% of the universe's total energy content, dwarfing even dark matter in its influence. But what exactly is dark energy? The truth is, we don't fully know. One leading theory is the cosmological constant, an idea first proposed by Albert Einstein. This theory suggests that dark energy is a property of space itself, a constant energy density that fills the vacuum of space and drives expansion. Another intriguing possibility is quintessence, a dynamic field that changes over time and could explain why the expansion rate of the universe varies. However, neither theory has been proven, and dark energy remains one of the most profound mysteries in cosmology. The implications of dark energy are staggering. If it continues to dominate the universe, it could lead to a future where galaxies drift so far apart that they become invisible to one another, leaving the cosmos cold, dark, and empty. As we continue to study this mysterious force, we are reminded that the universe is far more complex and mysterious than we ever imagined. With dark energy, we are not just exploring the unknown, we are confronting a force that could shape the ultimate fate of the cosmos. Now turning to the third phenomenon on our list, we encounter a gravitational mystery that has puzzled astronomers for decades, the Great Attractor. This enigmatic force is pulling galaxies, including our own Milky Way, toward a specific region of space at an astonishing speed of over 600 kilometers per second. But what exactly is this cosmic tug, and why is it so difficult to study? The Great Attractor lies in the direction of the constellation Centaurus, but its exact location is obscured by what astronomers call the zone of avoidance. This region of the sky is heavily shrouded by interstellar dust and stars from the plane of our galaxy, making it incredibly challenging to observe. Imagine trying to see through a thick fog. This is the obstacle astronomers face when studying the Great Attractor. Despite these challenges, advancements in technology such as infrared and radio telescopes have allowed us to peer through the dust and gather clues about this mysterious force. So, what could the Great Attractor be? One leading theory suggests it is a massive cluster of galaxies, so dense and massive that its gravitational pull influences the motion of galaxies across vast distances. This cluster, known as the Norma cluster, is thought to be at the heart of the Great Attractor. However, some researchers believe there could be something even more exotic at play, such as a supercluster of galaxies or an unseen concentration of dark matter exerting its influence. The implications of the Great Attractor are profound. It not only shapes the movement of galaxies but also offers insights into the large-scale structure of the universe. By studying this gravitational anomaly, we gain a deeper understanding of how matter is distributed across the cosmos and how these distributions influence the evolution of galaxies. Yet, despite decades of research, the true nature of the Great Attractor remains elusive, reminding us that the universe still holds many secrets waiting to be uncovered. As we continue to explore this cosmic mystery, we are drawn ever closer to unraveling the forces that shape our universe on the grandest scales. Now turning to the fourth phenomenon on our list, we delve into the enigmatic world of fast radio bursts or FRB. These are incredibly brief but intensely powerful bursts of radio waves that originate from distant galaxies, often billions of light-years away. First discovered in 2007, FRBs last only a few milliseconds, yet they release as much energy as the Sun does in several days. The sheer power and fleeting nature of these bursts have made them one of the most intriguing mysteries in modern astronomy. One of the biggest challenges with FRBs is pinpointing their exact sources. Because they last for such a short time and come from such vast distances, identifying their origins has proven to be a monumental task. However, advancements in radio telescope technology, such as the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, have allowed astronomers to detect and study these bursts with greater precision. In recent years, some FRBs have been traced back to specific galaxies, offering tantalizing clues about their origins. So, what could be causing these mysterious bursts? One leading theory suggests that FRBs are the result of cataclysmic events, such as the collision of neutron stars or the collapse of highly magnetized neutron stars known as magnetars. These violent cosmic events could produce the immense energy required to generate such bursts. Another, more speculative theory proposes that FRBs could be evidence of advanced extraterrestrial technology. While this idea captures the imagination, most scientists lean toward natural explanations, given the lack of repeatable patterns or signals that would suggest intelligent design. Recent discoveries have added even more layers to the mystery. some FRBs have been observed repeating with the same source emitting multiple bursts over time. This has led to new questions about what could cause such repetitive behavior. Could it be a natural process like a magnetar undergoing periodic outbursts, or something entirely different? Ongoing research efforts aim to uncover more about these repeating FRBs and their potential implications for our understanding of the universe. The study of fast radio bursts not only challenges our knowledge of astrophysics, but also opens up new possibilities for exploring the cosmos. By unraveling the secrets behind these bursts, we may gain insights into the most extreme environments in the universe and the processes that shape them. As we continue to detect and analyze FRBs, we are reminded once again of the vastness of the unknown and the endless opportunities for discovery that lie beyond our current understanding. Now turning to the fifth phenomenon on our list, we encounter one of the most thought-provoking questions in astronomy, the Fermi Paradox. Named after physicist Enrico Fermi, this paradox highlights the striking contradiction between the high probability of extraterrestrial life existing in the universe and the complete lack of evidence for it. Given the sheer size of the cosmos, with its hundreds of billions of galaxies and trillions of stars, it seems almost certain that life should have emerged elsewhere. Yet, despite decades of searching, we have found no definitive signs of intelligent civilizations beyond Earth. So, where is everyone? This question lies at the heart of the Fermi Paradox, and scientists have proposed several intriguing solutions to explain this cosmic silence. One of the most discussed ideas is the concept of the Great Filter. This theory suggests that there is some kind of barrier or event that prevents life from advancing to a stage where it can communicate across interstellar distances. The Great Filter could exist in our past, meaning that the emergence of intelligent life is extraordinarily rare, or it could lie in our future, implying that advanced civilizations inevitably destroy themselves before they can make contact. Another possibility is that intelligent life is simply exceedingly rare. While microbial life might be common in the universe, the conditions required for complex, intelligent life to evolve could be so specific that Earth is one of the very few places where it has happened. Alternatively, advanced civilizations might exist, but they are so far beyond our technological capabilities that we cannot detect them. They might communicate in ways we cannot yet understand or have chosen to remain hidden, perhaps to avoid interference with less developed species like us. Some scientists also suggest that advanced civilizations might not last long enough to make their presence known. Whether through self-destruction, resource depletion, or other existential threats, it is possible that intelligent life tends to extinguish itself before it can establish interstellar communication. This idea ties back to the Great Filter, emphasizing the fragility of technological civilizations. The Fermi Paradox challenges us to think deeply about our place in the universe and the future of humanity. Are we alone, or are we simply not looking in the right way? As we continue to search for signs of extraterrestrial life, from scanning the skies for radio signals to exploring the potential for life on distant exoplanets, the answers to this paradox may reshape our understanding of life, intelligence, and the cosmos itself. The mystery of the Fermi Paradox reminds us that, even as we explore the stars, some of the greatest questions remain unanswered. Now turning to the sixth phenomenon on our list, we delve into one of the most tantalizing mysteries in the search for extraterrestrial intelligence, the WOW signal. Detected on August 15, 1977, by the Big Ear Radio Telescope at Ohio State University, this signal remains one of the strongest and most enigmatic pieces of evidence in the quest to find life beyond Earth. The signal lasted for 72 seconds and was so remarkable that astronomer Jerry Amon circled it on the printout and wrote "WOW" next to it, giving the signal its iconic name. The WOW signal was a narrowband radio signal, meaning it was concentrated at a specific frequency, which is unusual for natural cosmic phenomena. It was detected at a frequency of 1,420 MHz, a range that is often used for interstellar communication because it is relatively free of interference from natural sources. This has led many to speculate that the signal could have been artificial in origin, possibly a deliberate transmission from an intelligent civilization. Despite its intriguing characteristics, the WOW signal has never been detected again. Numerous attempts have been made to find a repeat signal using more advanced telescopes, but none have succeeded. This has fueled ongoing debate about its origin. Some scientists argue that it could have been a natural event, such as a comet or a passing satellite, while others believe it remains one of the strongest candidates for evidence of extraterrestrial intelligence. The mystery of the WOW signal continues to captivate astronomers and the public alike. It serves as a reminder of how little we know about the universe and the potential for life beyond our planet. As we continue to scan the skies for signs of intelligent life, the WOW signal stands as a tantalizing clue that we may not be alone, and that the answers to some of our greatest questions could still be out there waiting to be discovered. Now turning to the seventh phenomenon on our list, we encounter one of the most perplexing stars in the cosmos, Tabby's star, also known as KIC 8462852. Located approximately 1,400 light-years away in the constellation Cygnus, this star has baffled astronomers with its bizarre and irregular dimming patterns. Unlike most stars, which dim in predictable ways due to orbiting planets or natural stellar processes, Tabby's star experiences sudden and dramatic drops in brightness, sometimes by as much as 22%, that defy easy explanation. The mystery began in 2015 when citizen scientists analyzing data from NASA's Kepler Space Telescope noticed these unusual fluctuations. The star's behavior was so strange that it sparked a flurry of scientific interest and speculation. One of the leading theories suggests that massive clouds of dust or debris orbiting the star could be causing the dimming. However, the irregularity and scale of the dimming events make even this explanation difficult to fully accept. Another, more provocative theory proposes that the dimming could be caused by an alien megastructure, such as a Dyson sphere, a hypothetical construct designed by an advanced civilization to harness the energy of a star. While this idea captures the imagination, most scientists remain skeptical, emphasizing the need for more evidence before jumping to such extraordinary conclusions. Other possibilities include swarms of comets, remnants of a shattered planet, or even a young star surrounded by a dense, clumpy disk of material. Despite years of observation and analysis, Tabby's star continues to resist a definitive explanation. Its unpredictable dimming patterns challenge our understanding of stellar behavior and remind us that the universe is full of surprises. As astronomers continue to study this enigmatic star, it serves as a humbling reminder of how much we still have to learn about the cosmos. With each new observation, we inch closer to unraveling the mystery, but for now, Tabby's star remains one of the most intriguing puzzles in the night sky. Now turning to the eighth phenomenon on our list, we delve into the mystery of the Pioneer Anomaly. This puzzling discovery involves the unexpected deceleration of the Pioneer 10 and Pioneer 11 spacecraft as they traveled through the outer reaches of our solar system. Launched in the early 1970s, these spacecraft were designed to explore the outer planets and beyond, but their trajectories revealed something scientists couldn't initially explain. As the spacecraft moved farther from the Sun, they began to slow down slightly more than predicted by the laws of gravity and known forces. This tiny but consistent deviation, measured at about 300 billionths of a meter per second squared, became known as the Pioneer Anomaly. At first, scientists suspected that the anomaly might be due to a simple oversight, such as an unaccounted-for force or a miscalculation in the spacecraft's design. However, even after extensive analysis, the cause remained elusive. One of the leading explanations points to thermal radiation. The spacecraft's nuclear power sources emitted heat, which could have created a tiny but measurable push against the spacecraft, causing the observed deceleration. While this theory seems plausible, it doesn't fully account for the anomaly's magnitude, leaving room for doubt. Another possibility is that the Pioneer Anomaly hints at new physics, perhaps a subtle modification to our understanding of gravity or the influence of dark matter in the outer solar system. Despite decades of investigation, the Pioneer Anomaly remains unresolved. It serves as a reminder that even our most advanced technologies and theories can encounter unexpected challenges when probing the depths of space. As scientists continue to explore this mystery, the Pioneer Anomaly stands as a testament to the complexity of the cosmos and the enduring quest to uncover its secrets. With each new discovery, we edge closer to understanding the forces that shape our universe, but for now, the Pioneer Anomaly remains a tantalizing enigma. Now turning to the 9th phenomenon on our list, we explore the mystery of the Oumuamua object. This interstellar visitor, first detected in October 2017, became the first known object from another star system to pass through our solar system. Its name, Oumuamua, means scout or messenger from afar in Hawaiian, and it certainly lived up to its name by sparking intense curiosity and debate among scientists. What made Oumuamua so extraordinary was its unusual shape and behavior. Unlike most asteroids or comets, which are roughly spherical or irregular, Oumuamua appeared to be elongated, resembling a cigar or a pancake. Its shape was estimated to be about 10 times longer than it was wide, a feature rarely seen in natural objects. Even more intriguing was its acceleration as it moved away from the Sun. While most objects slow down as they leave the Sun's gravitational pull, Oumuamua sped up slightly, defying expectations. This unexpected acceleration led to a flurry of theories. Some scientists suggested that Oumuamua might be a comet, with outgassing the release of gas as it warmed, providing the extra push. However, no visible coma or tail, typical signs of outgassing, were observed. Others proposed that Oumuamua could be a fragment of a larger object, shattered by a collision in its home system. But the most controversial idea came from those who speculated that Oumuamua might not be a natural object at all. Could it be an alien probe, perhaps a solar sail or a piece of extraterrestrial technology? While this idea captured the public's imagination, most scientists remained skeptical, emphasizing the need for more evidence. Despite its brief visit, Oumuamua left a lasting impact on our understanding of the cosmos. It challenged our assumptions about the nature of interstellar objects and reminded us that the universe is full of surprises. As we continue to search for answers, Oumuamua remains a fascinating enigma, a fleeting glimpse into the mysteries that lie beyond our solar system. With each new discovery, we inch closer to unraveling the secrets of the universe, but for now, Oumuamua stands as a reminder of how much we have yet to learn. Now turning to the 10th phenomenon on our list, we delve into the mystery of the axis of evil. This peculiar alignment in the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang, has puzzled scientists since its discovery. The cosmic microwave background is a snapshot of the universe when it was just 380,000 years old, and it provides crucial insights into the early universe's structure and composition. However, the axis of evil presents a strange anomaly that challenges one of the fundamental principles of cosmology, the cosmological principle. The cosmological principle states that the universe is homogeneous and isotropic on large scales, meaning it should look the same in all directions. But the axis of evil defies this expectation. It refers to an unexpected alignment of temperature fluctuations in the cosmic microwave background, suggesting a preferred direction in the universe. This alignment appears to point toward a specific axis, as if the universe has a preferred orientation, which contradicts the idea that the cosmos is uniform and without a central structure. The implications of this discovery are profound. If the axis of evil is real and not a statistical fluke or an artifact of measurement, it could force us to rethink our understanding of the universe's origins and evolution. Some theories propose that this alignment might be evidence of a pre-Big Bang structure or the influence of a multiverse. Others suggest it could be linked to the mysterious dark energy driving the universe's accelerated expansion. However, no definitive explanation has been found, and the axis of evil remains one of the most perplexing mysteries in modern cosmology. Ongoing research aims to determine whether this alignment is a genuine feature of the universe or simply a result of observational bias or incomplete data. Future missions, such as those designed to map the cosmic microwave background with even greater precision, may shed light on this enigma. For now, the axis of evil serves as a reminder that even our most fundamental assumptions about the cosmos can be called into question, urging us to keep exploring and questioning the nature of reality. As we move forward, this phenomenon continues to challenge our understanding and inspire new avenues of scientific inquiry. Now turning to the 11th phenomenon on our list, we explore the enigmatic black hole information paradox. This paradox lies at the heart of one of the most profound debates in modern physics, challenging our understanding of black holes and the fundamental laws of the universe. At its core, the paradox revolves around a simple yet perplexing question: what happens to information that falls into a black hole? According to classical physics, once something crosses a black hole's event horizon, the point of no return, it is lost forever, crushed into the singularity at the center. However, quantum mechanics tells us that information cannot be destroyed. It must be preserved in some form. This creates a direct conflict between two of the most successful theories in physics: general relativity, which governs the behavior of black holes, and quantum mechanics, which governs the behavior of particles at the smallest scales. The paradox gained prominence in the 1970s when Stephen Hawking proposed that black holes emit radiation, now known as Hawking radiation. This radiation, he argued, would cause black holes to slowly lose mass and eventually evaporate entirely. But here's the catch: Hawking radiation appears to be random, carrying no information about the matter that fell into the black hole. If the black hole evaporates completely, the information about the original matter would seemingly be lost forever, violating the principles of quantum mechanics. This dilemma has sparked decades of debate and inspired groundbreaking theories. Some physicists, including Hawking himself, initially believed that information was indeed lost, suggesting that our understanding of quantum mechanics might need revision. Others, however, argue that information must somehow escape the black hole, perhaps encoded in the Hawking radiation or preserved in some other form. This idea led to the development of concepts like the holographic principle, which suggests that all the information about objects falling into a black hole could be stored on its event horizon like a cosmic hard drive. Despite these efforts, the black hole information paradox remains unresolved. It challenges us to reconcile the seemingly incompatible worlds of quantum mechanics and general relativity, hinting at the need for a more complete theory of quantum gravity. As scientists continue to probe this mystery, the paradox serves as a reminder of how much we still have to learn about the universe's most extreme environments. With each new discovery, we inch closer to unraveling the secrets of black holes and the fate of the information they consume. Now turning to the 12th phenomenon on our list, we delve into the mystery of the moon's origin. For centuries, the moon has captivated humanity, but how it came to be remains one of the most intriguing questions in planetary science. The leading theory, known as the giant impact hypothesis, suggests that the moon formed from the debris of a colossal collision between Earth and a Mars-sized protoplanet, often referred to as Theia, around 4.5 billion years ago. This cataclysmic event would have ejected a massive amount of material into orbit around Earth, which eventually coalesced to form the moon. While this theory explains many aspects of the Earth-Moon system, such as the Moon's relatively large size compared to Earth and its lack of volatile elements, it also faces significant challenges. One of the most puzzling issues is the striking similarity in isotopic compositions between Earth and the Moon. Isotopes are like chemical fingerprints, and the fact that Earth and the Moon share nearly identical isotopic ratios for elements like oxygen suggests they originated from the same material. This is difficult to reconcile with the idea that Theia, a separate body, contributed significantly to the Moon's formation. If Theia had a different isotopic signature, as expected, the Moon should reflect a mix of both Earth and Theia's compositions, but it doesn't. Another challenge lies in the Moon's composition. While the giant impact hypothesis explains the Moon's lack of water and other volatile elements, it struggles to account for the precise chemical and mineralogical similarities between Earth and the Moon. Some scientists have proposed variations of the hypothesis, such as a faster spinning early Earth or multiple smaller impacts, but none have fully resolved these inconsistencies. The mystery of the Moon's origin continues to drive research and debate. Recent studies using advanced computer simulations and high-precision measurements of lunar rocks have provided new insights, but the puzzle remains incomplete. Understanding how the Moon formed not only sheds light on Earth's early history, but also offers clues about the formation of other planetary systems. As we explore this enduring enigma, we are reminded of the complex and dynamic processes that shaped our solar system and the questions that still await answers. Now turning to the 13th phenomenon on our list, we explore the Tunguska event, one of the most dramatic and mysterious explosions in recorded history. On June 30, 1908, a massive explosion rocked the remote forests of Siberia near the Tunguska River. The blast was so powerful that it flattened an estimated 80 million trees over an area of more than 2,000 square kilometers, and its shockwave was felt hundreds of kilometers away. Eyewitnesses reported seeing a bright fireball streaking across the sky, followed by a deafening roar and a series of intense heat waves. Despite the scale of the devastation, no impact crater was ever found, leaving scientists puzzled for over a century. The leading theory suggests that the Tunguska event was caused by the airburst of a meteoroid or comet. As the object entered Earth's atmosphere at high speed, the intense pressure and heat caused it to explode several kilometers above the ground. This type of explosion, known as an airburst, can release energy equivalent to hundreds of nuclear bombs, explaining the widespread destruction. However, because the object disintegrated in the atmosphere, no solid remnants reached the ground to form a crater. This theory is supported by the lack of a crater and the pattern of tree fall, which radiates outward from a central point consistent with an aerial explosion. Another possibility is that the object was a comet composed primarily of ice and dust, which would have vaporized completely upon entering the atmosphere. This could explain the absence of large fragments or a crater. However, the lack of definitive evidence, such as chemical traces or debris, has made it difficult to confirm this hypothesis. Some researchers have even proposed more exotic explanations, such as a small black hole passing through Earth or the release of natural gas from the ground, though these ideas remain speculative and lack strong evidence. The Tunguska event continues to captivate scientists and the public alike, not only because of its sheer scale, but also because it highlights the potential dangers posed by near-Earth objects. If a similar event were to occur over a populated area today, the consequences could be catastrophic. This mystery serves as a reminder of the dynamic and sometimes unpredictable nature of our solar system, and the importance of monitoring and understanding the objects that share our cosmic neighborhood. As we move forward, the Tunguska event remains a key case study in planetary defense and a testament to the enduring mysteries of our universe. Now turning to the 14th phenomenon on our list, we delve into the enigmatic zodiacal light, a subtle yet captivating glow that graces the night sky. This faint pyramid-shaped light is most visible just after sunset or before sunrise, appearing as a soft, diffuse band stretching upward from the horizon. The zodiacal light is caused by sunlight reflecting off countless tiny particles of interplanetary dust scattered throughout the inner solar system. These dust particles, often no larger than grains of sand, are thought to be remnants of comets, asteroids, and collisions between larger bodies. Despite its beauty, the zodiacal light presents a significant mystery to astronomers. According to theoretical models, the amount of dust required to produce this glow should be much greater than what we actually observe. This discrepancy has led scientists to question where all the missing dust might be. One possibility is that the dust is being continuously replenished by comets and asteroids, but even this explanation doesn't fully account for the observed deficit. Another theory suggests that the dust particles might be smaller or more reflective than previously thought, making them harder to detect but still capable of producing the zodiacal light. Adding to the mystery, recent observations have revealed that the distribution of this interplanetary dust is not uniform. Instead, it appears to be concentrated in certain regions, possibly influenced by the gravitational pull of planets or the remnants of ancient collisions. Some researchers have even proposed that the dust could be part of a larger, yet undiscovered, structure within the solar system, such as a faint ring or cloud of material. The zodiacal light not only challenges our understanding of the solar system's composition, but also serves as a reminder of the dynamic processes that shape our cosmic environment. As we continue to study this phenomenon, it offers valuable insights into the origins and evolution of the dust that fills the space between planets. With each new discovery, we come closer to unraveling the secrets of this celestial glow. Yet the zodiacal light remains a testament to the enduring mysteries that await us in the vast expanse of space. Now turning to the 15th phenomenon on our list, we encounter the intriguing mystery of the Kuiper Cliff. This sudden and unexpected drop-off in the number of objects within the Kuiper Belt has left astronomers scratching their heads. The Kuiper Belt, a vast region of icy bodies beyond Neptune, is home to countless objects, including dwarf planets like Pluto. However, at a certain distance from the Sun, the number of these objects dramatically decreases, creating what scientists call the Kuiper Cliff. Theories about the cause of this abrupt boundary vary widely. One leading hypothesis suggests the presence of an undiscovered planet lurking in the outer reaches of the solar system. This hypothetical planet, often referred to as Planet 9, could have gravitationally cleared out objects in its path, creating the observed drop-off. While no direct evidence of Planet 9 has been found, its existence would explain not only the Kuiper Cliff but also the unusual orbits of some distant objects. Another possibility is that the Kuiper Cliff is the result of a massive collision in the distant past. Such an event could have scattered debris across the solar system, leaving behind a noticeable gap in the Kuiper Belt. Alternatively, the cliff might mark the edge of the primordial disk of material from which the solar system formed, suggesting that the Kuiper Belt's current structure is a relic of its early history. The Kuiper Cliff challenges our understanding of the solar system's formation and evolution. It raises questions about the processes that shape the outer regions of our cosmic neighborhood and whether there are still hidden worlds waiting to be discovered. As astronomers continue to study this enigmatic boundary, it serves as a reminder of how much we have yet to learn about the vast and dynamic expanse of space. With each new observation, we edge closer to unraveling the secrets of the Kuiper Cliff and the mysteries it holds. Now turning to the 16th phenomenon on our list, we delve into the perplexing mystery known as the Hubble tension. This cosmic conundrum revolves around a discrepancy in measurements of the universe's expansion rate, a fundamental parameter in cosmology. The expansion rate, often referred to as the Hubble constant, is crucial for understanding the age, size, and future of our universe. However, scientists have found that different methods of measuring this rate yield conflicting results, creating a tension that challenges our understanding of the cosmos. One method involves observing distant supernovae and using them as cosmic mile markers to calculate the expansion rate. Another approach relies on studying the cosmic microwave background radiation, the faint afterglow of the Big Bang, which provides a snapshot of the early universe. While both methods are highly precise, they consistently produce different values for the Hubble constant. This inconsistency has left astronomers puzzled and has sparked intense debate within the scientific community. The implications of the Hubble tension are profound. If the discrepancy is due to observational errors or overlooked factors in our measurements, it could mean that our current understanding of the universe is incomplete. On the other hand, if the tension points to new physics beyond our current models, it could revolutionize cosmology. Some theories suggest the existence of unknown forms of dark energy or dark matter that could be influencing the expansion rate in unexpected ways. Others propose modifications to Einstein's theory of general relativity to account for the observed differences. Efforts to resolve the Hubble tension are ongoing, with astronomers refining their measurement techniques and exploring new observational tools. Space telescopes like the James Webb Space Telescope and ground-based observatories are being used to gather more precise data, while theoretical physicists are developing innovative models to explain the discrepancy. The resolution of this tension could provide deeper insights into the nature of the universe and its ultimate fate. The Hubble tension serves as a reminder that even the most well-established scientific principles can be challenged by new discoveries. It highlights the dynamic and ever-evolving nature of our quest to understand the cosmos. As we continue to explore this mystery, we are reminded that the universe is full of surprises, and each unanswered question brings us closer to uncovering its deepest secrets. Now turning to the 17th phenomenon on our list, we encounter the missing baryon problem, a cosmic puzzle that challenges our understanding of the universe's composition. Baryons are the building blocks of ordinary matter, including protons and neutrons, which make up stars, planets, and everything we see around us. According to the Big Bang theory, the universe should contain a specific amount of baryonic matter. However, when astronomers tally up all the observable baryons, they find that a significant portion is missing. This discrepancy has led scientists on a quest to locate the missing baryons, often referred to as the missing matter problem. One leading theory suggests that these baryons exist in the form of a diffuse, hot gas known as the warm-hot intergalactic medium, or WIM. This elusive material is thought to reside in the vast spaces between galaxies, where it is too faint and spread out to be easily detected. The WIM is believed to consist of ionized gas, heated to temperatures of hundreds of thousands to millions of degrees, making it invisible to traditional optical telescopes. To uncover this hidden matter, astronomers have turned to advanced techniques and instruments. X-ray telescopes, such as the Chandra X-ray Observatory, have been instrumental in detecting the faint signatures of the WIM. By observing the absorption of X-rays as they pass through intergalactic space, scientists can infer the presence of this hot gas. Additionally, ultraviolet observations have provided further clues, as the WIM absorbs certain wavelengths of light from distant quasars and galaxies. Despite these efforts, the search for the missing baryons remains ongoing. The challenge lies in the fact that the WIM is incredibly diffuse and difficult to observe directly. However, recent advancements in technology and observational methods are bringing us closer to solving this mystery. For instance, upcoming missions like the European Space Agency's Athena X-ray Observatory aim to map the WIM in greater detail, potentially revealing the location of the missing baryons. The missing baryon problem underscores the complexity of the universe and the limitations of our current observational capabilities. It reminds us that even the most fundamental aspects of the cosmos can hold surprises, and that our understanding is continually evolving. As we continue to search for these elusive particles, we are reminded that the universe is far more intricate and mysterious than we often imagine. Each discovery brings us closer to piecing together the full picture of the cosmos, one baryon at a time. Now turning to the 18th phenomenon on our list, we delve into the galactic center excess, a mysterious surge of gamma-ray radiation emanating from the heart of our Milky Way galaxy. This excess radiation, first detected by NASA's Fermi Gamma-Ray Space Telescope, has puzzled scientists for years. While the galactic center is known to be a bustling hub of activity with stars, black holes, and other cosmic phenomena, the intensity of this gamma-ray glow exceeds what can be explained by known sources. One leading theory suggests that this excess radiation could be the result of dark matter annihilation. According to this idea, dark matter particles, which are thought to make up a significant portion of the universe's mass, could collide and annihilate each other, releasing gamma rays in the process. The galactic center, with its high concentration of dark matter, would be a prime location for such interactions. If this theory holds true, it could provide crucial evidence for the existence of dark matter and help us understand its properties. However, not all scientists are convinced. Another explanation points to pulsars, rapidly rotating neutron stars that emit beams of radiation. These celestial objects could be responsible for the gamma-ray excess, especially if there is a large population of them near the galactic center. Pulsars are known to produce gamma rays, and their combined emissions might account for the observed glow. Yet, identifying and counting these pulsars has proven to be a significant challenge, leaving this theory unresolved. Adding to the mystery is the difficulty in distinguishing between these competing explanations. The gamma-ray signals from dark matter annihilation and pulsars can appear remarkably similar, making it hard to determine which one is the true source. Advanced observational techniques and new data from telescopes are being employed to untangle this cosmic puzzle, but so far, the galactic center excess remains unexplained. This phenomenon highlights the complexity of our galaxy's core and the challenges of studying it. It also underscores the importance of continued exploration and innovation in astrophysics. As we strive to uncover the secrets of the galactic center, we are reminded that even the most familiar parts of the universe can hold surprises, pushing the boundaries of our knowledge and inspiring us to look deeper into the cosmos. Now turning to the 19th phenomenon on our list, we explore the Eridanus supervoid, an enormous and mysterious region of space that defies our expectations. Stretching across an area of the universe roughly 1 billion light-years wide, this supervoid is strikingly empty, containing far fewer galaxies than scientists would predict based on the distribution of matter in the cosmos. Its sheer size and emptiness make it one of the most intriguing anomalies in the universe. What makes the Eridanus supervoid even more fascinating is its potential connection to the cold spot, a peculiar feature in the cosmic microwave background radiation. The cold spot is a region of the sky where the temperature of the radiation left over from the Big Bang is slightly lower than the surrounding areas. While small temperature variations are common in the cosmic microwave background, the cold spot stands out due to its size and intensity. Some scientists believe that the Eridanus supervoid could be responsible for this anomaly. The idea is that as light travels through the supervoid, it loses energy due to the expansion of the universe, a process known as the integrated Sachs-Wolfe effect. This could explain why the cold spot appears colder than its surroundings. However, this explanation is not without controversy. The Eridanus supervoid, while vast, may not be large enough to fully account for the cold spot's temperature drop. Additionally, the supervoid's existence challenges our understanding of how matter is distributed in the universe. According to the standard model of cosmology, such enormous voids should be extremely rare, yet the Eridanus supervoid exists, raising questions about whether our models need revision. Another challenge lies in the difficulty of studying the supervoid itself. Its immense size and the faintness of the galaxies within it make observations incredibly complex. Astronomers rely on advanced telescopes and surveys to map its structure, but even with these tools, the supervoid's true nature remains elusive. Some researchers have proposed alternative explanations for the cold spot, such as cosmic textures or even exotic physics beyond our current understanding. The Eridanus supervoid and its connection to the cold spot remind us that the universe is full of surprises. They challenge our assumptions about the large-scale structure of the cosmos and push us to refine our theories. As we continue to study these phenomena, we are reminded that the universe is far more complex and mysterious than we often imagine, and that every discovery brings us closer to unraveling its deepest secrets. Now turning to the 20th phenomenon on our list, we delve into the intriguing hypothesis of a ninth planet lurking in the outer reaches of our solar system. Known as Planet 9, this hypothetical world has captured the imagination of astronomers and the public alike, as it could explain some of the strange behaviors observed in the distant Kuiper belt. The idea of Planet 9 emerged from the peculiar clustering of certain Kuiper belt objects, small icy bodies that orbit the Sun beyond Neptune. These objects exhibit unusual orbital patterns, with their paths tilted and elongated in ways that suggest the gravitational influence of a massive, unseen object. Scientists hypothesize that a planet roughly 10 times the mass of Earth could be responsible for these anomalies, pulling these objects into their strange orbits as it moves through the outer solar system. The search for Planet 9 has been a challenging endeavor. Its proposed location is so far from the Sun that it would reflect very little light, making it incredibly difficult to detect with current telescopes. Additionally, its orbit is thought to be highly elliptical, meaning it could take thousands of years to complete a single trip around the Sun. This makes pinpointing its exact position a daunting task. Despite these challenges, astronomers have been using advanced sky surveys and computer simulations to narrow down the possible locations where Planet 9 might be hiding. One of the most compelling pieces of evidence for Planet 9 comes from the work of astronomers Konstantin Batygin and Mike Brown, who first proposed the hypothesis in 2016. Their simulations showed that the gravitational effects of a distant planet could explain not only the clustering of Kuiper belt objects, but also the unusual tilt of the solar system's plane. While the evidence is indirect, it has sparked a wave of interest and research, with scientists around the world joining the hunt for this elusive world. The discovery of Planet 9, if it exists, would be a monumental achievement in astronomy. It would not only reshape our understanding of the solar system's architecture, but also provide new insights into the formation and evolution of planetary systems. For now, the search continues, driven by the tantalizing possibility that a hidden giant is waiting to be found in the icy depths of our cosmic neighborhood. As we explore this hypothesis, we are reminded once again that the universe is full of mysteries, and that even our own solar system still holds secrets waiting to be uncovered. Now turning to the 21st phenomenon on our list, we explore one of the most perplexing mysteries of our own star, the Sun. The solar corona, the outermost layer of the Sun's atmosphere, is millions of degrees hotter than the Sun's surface, a fact that defies our basic understanding of heat and energy. This enigma, known as the solar corona heating problem, has puzzled scientists for decades, and despite significant advancements in solar physics, it remains unresolved. At first glance, it seems counterintuitive. The Sun's surface, or photosphere, has a temperature of around 5,500 degrees Celsius, while the corona, which lies millions of kilometers above it, soars to temperatures of 1 to 3 million degrees Celsius. Why does the outer layer of the Sun's atmosphere get hotter as you move away from its core? This question has led to a flurry of research and a range of compelling theories. One leading explanation involves magnetic reconnection. a process where the sun's magnetic field lines twist, break, and reconnect, releasing enormous amounts of energy. This energy is thought to heat the corona, creating the extreme temperatures observed. Another theory points to nanoflares, tiny but frequent bursts of energy that occur across the sun's surface. These miniature explosions, though individually small, could collectively contribute enough heat to explain the corona's scorching temperatures. However, proving these theories has been a significant challenge. The sun's corona is a dynamic and chaotic environment, making it difficult to observe and measure the processes at play. Advanced instruments like NASA's Parker Solar Probe, which flies closer to the sun than any previous mission, are providing unprecedented data. Yet, even with these cutting-edge tools, the exact mechanisms behind the corona's heating remain elusive. The solar corona heating problem is not just an academic curiosity. Understanding it could shed light on fundamental processes in plasma physics and help us predict solar activity, such as solar flares and coronal mass ejections, which can impact Earth's technology and communication systems. As scientists continue to probe this mystery, they are reminded of the complexity and wonder of the star that powers our solar system. The sun, so familiar and yet so enigmatic, continues to challenge our understanding, proving that even the closest celestial bodies hold secrets waiting to be unraveled. Now turning to the 22nd phenomenon on our list, we delve into the mystery of galaxy rotation curves, a puzzle that has reshaped our understanding of the cosmos. When astronomers study how galaxies rotate, they expect the outer regions to move slower than the inner ones, much like planets in our solar system. However, observations reveal something entirely different. Stars and gas in the outer regions of galaxies move at nearly the same speed as those closer to the center. This unexpected behavior defies the predictions based on the visible matter we can see, such as stars, gas, and dust. This discrepancy is known as the galaxy rotation curve problem, and it has profound implications for our understanding of the universe. If the visible matter were the only source of gravity, the outer regions of galaxies should slow down dramatically, but they don't. This suggests that there's something else at play, something invisible yet massive enough to influence the motion of stars and gas. Enter dark matter, the mysterious substance that makes up about 85% of the universe's total mass. Dark matter doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet its gravitational effects are undeniable, and it's the leading explanation for the observed rotation curves of galaxies. The idea of dark matter was first proposed in the 1930s by Swiss astronomer Fritz Zwicky, but it gained widespread acceptance in the 1970s when Vera Rubin and her colleagues provided compelling evidence through their observations of galaxy rotation. Since then, dark matter has become a cornerstone of modern cosmology, helping to explain not only galaxy rotation but also the large-scale structure of the universe and the behavior of galaxy clusters. However, the search for dark matter is far from over. Despite decades of research, scientists have yet to directly detect it. Experiments like those using underground detectors, particle colliders, and space-based observatories are ongoing, but so far, dark matter remains elusive. This has led some researchers to explore alternative explanations, such as modified Newtonian dynamics, or MUND, which proposes tweaking the laws of gravity to account for the observed rotation curves without invoking dark matter. While MUND has had some success in explaining certain phenomena, it struggles to account for all the evidence that supports dark matter's existence. The galaxy rotation curve problem is a reminder of how much we still have to learn about the universe. It challenges us to rethink our assumptions about gravity, matter, and the very fabric of reality. As scientists continue to investigate this mystery, they are not only seeking to understand the nature of dark matter, but also pushing the boundaries of our knowledge, revealing the profound complexity of the cosmos. The rotation of galaxies, once thought to be a straightforward phenomenon, has become a window into the hidden forces that shape our universe. Now turning to the 23rd phenomenon on our list, we encounter the cosmic lithium problem, a puzzle that challenges our understanding of the early universe. According to the Big Bang nucleosynthesis theory, the first few minutes after the Big Bang produced light elements like hydrogen, helium, and lithium in specific amounts. While the observed abundances of hydrogen and helium match the predictions almost perfectly, lithium presents a glaring inconsistency. The amount of lithium we see in the universe today is only about 1/3 of what the theory predicts. This discrepancy has left scientists scratching their heads for decades. The cosmic lithium problem is particularly intriguing because it suggests that something fundamental is missing from our understanding of the early universe or the processes that followed. One possible explanation lies in stellar processes. Stars, especially older ones, can destroy or alter lithium over time through nuclear reactions in their cores. This could mean that the lithium produced in the Big Bang was gradually depleted as stars formed and evolved. However, this explanation doesn't fully account for the observed deficit, leaving room for other possibilities. Another avenue of exploration involves new physics. Some researchers propose that our current models of the Big Bang nucleosynthesis might be incomplete, or that unknown particles or interactions could have influenced the production or destruction of lithium in the early universe. For instance, certain theories suggest that hypothetical particles like actions or changes in the fundamental constants of nature could have played a role. While these ideas are speculative, they highlight the need for innovative thinking to solve this cosmic mystery. The cosmic lithium problem is more than just a numbers game. It's a window into the earliest moments of the universe and the processes that shaped it. Solving this puzzle could provide insights into the nature of dark matter, the behavior of stars, or even the fundamental laws of physics. As astronomers and physicists continue to study this phenomenon, they are not only seeking to reconcile the lithium discrepancy, but also uncovering deeper truths about the cosmos. The cosmic lithium problem reminds us that even the smallest elements can hold the key to understanding the grandest mysteries of the universe. Now turning to the 24th phenomenon on our list, we encounter the Red Rectangle Nebula, a striking and enigmatic structure in the cosmos. Located about 2,300 light-years away in the constellation Monoceros, this nebula stands out for its unusual geometric shape and vivid red hue. Unlike most nebulae, which appear as swirling clouds of gas and dust, the red rectangle boasts a distinct rectangular appearance with ladder-like rungs of glowing material. This peculiar structure has fascinated astronomers since its discovery, and it remains one of the most visually captivating yet poorly understood objects in the universe. The Red Rectangle Nebula's unique shape is believed to be the result of interactions between a pair of binary stars at its center. One of these stars is in the late stages of its life, shedding layers of gas and dust into space. As this material is ejected, it is shaped by the gravitational forces and stellar winds of the binary system, creating the nebula's intricate rectangular form. The red color, on the other hand, is thought to come from a process called fluorescence, where ultraviolet light from the stars excites hydrogen molecules, causing them to emit a reddish glow. Despite these explanations, the Red Rectangle Nebula continues to puzzle scientists. For instance, the precise mechanisms behind its geometric symmetry and the formation of its ladder-like features are still unclear. Some researchers suggest that the nebula's shape could be influenced by a dense disk of dust surrounding the binary stars, which funnels the ejected material into a specific pattern. Others propose that the nebula's structure might be shaped by magnetic fields or other unseen forces. However, none of these theories fully account for the nebula's unique characteristics, leaving much to be explored. What makes the Red Rectangle Nebula even more intriguing is its potential connection to the formation of complex organic molecules. observations have revealed the presence of polycyclic aromatic hydrocarbons, or PAH, within the nebula. These molecules are considered building blocks for more complex organic compounds, raising questions about whether similar processes could occur in other regions of the universe, potentially contributing to the origins of life. While this idea is speculative, it adds another layer of mystery to the Red Rectangle Nebula and its role in the cosmos. The Red Rectangle Nebula serves as a reminder that even the most visually stunning objects in the universe can harbor profound mysteries. Its geometric perfection challenges our understanding of how cosmic structures form and evolve, while its chemical composition hints at processes that could have far-reaching implications. As astronomers continue to study this remarkable nebula, they are not only unraveling its secrets but also gaining insights into the broader workings of the universe. The Red Rectangle Nebula is a testament to the beauty and complexity of the cosmos, inviting us to ponder the countless wonders that remain hidden among the stars. Now turning to the 25th and final phenomenon on our list, we encounter the Boötes Void, one of the most mysterious and expansive regions of space ever discovered. Known as the Great Nothing, the Boötes Void is a colossal, nearly empty region of the universe, spanning an astonishing 330 million light-years across. Located in the constellation Boötes, this void contains only a handful of galaxies, making it one of the largest and most sparsely populated areas in the known cosmos. Its existence challenges our understanding of the universe's large-scale structure and raises profound questions about how such vast emptiness could form. The Boötes Void was first discovered in the 1980s during surveys of the universe's large-scale structure. Astronomers expected to find a relatively even distribution of galaxies, but instead they stumbled upon this enormous, nearly barren region. To put its size into perspective, if the Milky Way were placed at the center of the Boötes Void, we would not have known about the existence of other galaxies until the late 20th century. This staggering emptiness defies our expectations of how matter is distributed in the universe, as most regions of space are filled with galaxies, galaxy clusters, and cosmic filaments. One of the most puzzling aspects of the Boötes Void is how it came to exist in the first place. According to the standard model of cosmology, the universe's large-scale structure formed through the gravitational collapse of matter into dense regions, leaving behind less dense voids. However, the Boötes Void is far emptier than predicted by these models. Some scientists suggest that it could be the result of multiple smaller voids merging over billions of years, creating a single, vast emptiness. Others propose that it might be evidence of exotic physics, such as the influence of dark energy, or even the remnants of a collision between our universe and another in a hypothetical multiverse. Yet, none of these explanations fully account for the void's extreme sparsity. The Boötes Void also has significant implications for our understanding of the universe's evolution. Its existence suggests that the distribution of matter on the largest scales is far more uneven than previously thought. This challenges the cosmological principle, which states that the universe should look roughly the same in all directions when viewed on a large enough scale. If voids like Boötes are more common than we realize, it could mean that our current models of the universe's structure and evolution are incomplete or even fundamentally flawed. Despite its emptiness, the Boötes Void is not entirely devoid of interest. The few galaxies that do reside within it are often isolated and unique, offering astronomers a rare opportunity to study how galaxies evolve in such extreme environments. These galaxies may have formed under conditions vastly different from those in denser regions of the universe, providing insights into the diverse pathways of cosmic evolution. The Boötes Void serves as a humbling reminder of how much we still have to learn about the universe. Its vast emptiness challenges our assumptions and pushes the boundaries of our knowledge, inviting us to explore the unknown and rethink our understanding of the cosmos. As we conclude our journey through these 25 unexplained astronomical phenomena, the Boötes void stands as a symbol of the mysteries that still await us among the stars. It reminds us that the universe is full of surprises and that every discovery brings us closer to unraveling its deepest secrets. Now turning to the conclusion of our journey through the top 25 astronomical phenomena still unexplained by science, we are left in awe of the vast mysteries that the universe holds. From the enigmatic nature of dark matter and dark energy to the perplexing signals from distant stars and the mind-bending emptiness of the Boötes void, each phenomenon challenges our understanding and pushes the boundaries of human knowledge. These mysteries remind us that, despite our advancements, the cosmos remains a place of profound wonder and unanswered questions. These 25 phenomena highlight the limits of our current scientific frameworks. They show us that the universe is far more complex and unpredictable than we once imagined. Whether it's the unexplained dimming of Tabby's star, the strange acceleration of Oumuamua, or the eerie silence of the Fermi Paradox, each mystery invites us to question, explore, and rethink what we know. They are not just scientific puzzles, but also invitations to dream, to imagine, and to seek out the unknown. The importance of continued exploration cannot be overstated. Every discovery, no matter how small, brings us closer to understanding the universe's deepest secrets. It is through the tireless efforts of astronomers, physicists, and curious minds around the world that we inch closer to unraveling these cosmic enigmas. The journey is far from over, and the next breakthrough could be just around the corner. As we reflect on these wonders, we invite you to share your thoughts and theories in the comments below. What do you think lies behind these mysteries? Which phenomenon fascinates you the most? Let's continue the conversation and explore the universe together. If you enjoyed this journey through the cosmos, don't forget to subscribe and hit the notification bell for more space content. The universe is vast and its mysteries are endless, so let's keep exploring, questioning, and marveling at the wonders that await us among the stars. Thank you for joining us on this incredible adventure, and until next time, keep looking up.